Welcome to AP Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at the last few sections of Chapter 20. Now, first section, section 20.7, deals with looking at batteries and fuel cells, because we're talking about voltaic cells, and those are things that create energy. What way do we harness those in everyday life? Now, a battery is a portable, self-contained electrochemical power source. So you're basically using redox reactions in a spontaneous redox reaction to generate electricity, a flow of current. Now, when in series, that means hook up anode to cathode, the total EMF is the sum of the individual EMFs. So if we hook together our 1.5 volt batteries in series, we end up with overall 3.0 volts. This is a way in which we can couple batteries together to basically get a higher voltage. Now, a primary cell is one that can't be recharged. An example, that would be alkaline batteries. So one type of battery or voltaic cell would be one that's called a primary cell. Now, a secondary cell is a cell that can be recharged with an external power source. And NiCad batteries, lithium batteries, our car batteries, which are lead acid batteries. In each of those cases, we can use the battery to generate electricity, but if we push electricity through in reverse, then we undo basically our spontaneous reaction and we recharge our battery. So rechargeable batteries are what we call secondary batteries, and we use them a lot in everyday life. Your cell phone contains a secondary battery because it's a rechargeable battery. Now, lead acid batteries, which are the types of batteries that are in our automobiles, are really important in use in everyday life. Now, in order to operate your car, you really need to generate quite a bit of voltage. So basically you have 6 2-volt cells in series. And it's a secondary battery because the chemical reaction that gives us our electricity to start our car and run our radios and so forth is one that is reversible. Once you start the car, you basically harness the power of the moving pistons through an alternator to actually pass electricity back through the battery and recharge the battery so it's ready to keep going. Alkaline batteries, remember these were not secondary batteries. Alkaline batteries are not rechargeable. If you break them open, they kind of have this internal structure. You've got an anode at the bottom, that's why it's negatively charged, and a cathode at the top, positively charged. And what's typically in the cathode is manganese dioxide. And what's in our anode is a zinc plus a mixture of potassium hydroxide. So sometimes you'll end up with a D battery or a C battery in our alkaline batteries that some sort of liquid comes out of them when they go bad. A lot of times people, be careful, that's battery acid. Well, it's not an acid. It's actually a basic solution of potassium hydroxide. Still potentially damaging. You don't want to get it on you, but battery acid is the acid that we have inside our car batteries. That type of wet cell battery uses an acid medium. Here we've got a base medium with our zinc. Now, fuel cells, and this is something that you start hearing more about in the last few years, is the need for lowering our fossil fuel intake and coming up with cars that run on different types of batteries and cells. Fuel cell is unlike a battery, it's not a self-contained system. The need to supply a constant amount of fuel, hence the name fuel cell, to make electricity. So one thing that we can use as fuel would be normal gasoline. Well, if we're trying to cut down our fossil emissions, it'd be nice to come up with a fuel cell that uses something else. In this case, what we're using is, as our fuel, hydrogen gas. And the nice thing about this is, the hydrogen itself is not a fossil fuel. And when hydrogen comes together with oxygen, your exhaust products are basically oxygen and water. So one of the nice things about this fuel cell is it's a way to generate electricity to maybe move a car, and you end up with a fuel that's not a fossil fuel, and you have an exhaust that is significantly cleaner than what happens when we combust fossil fuels. So what we're looking at here is a type of situation where it's not self-contained. So basically, you just don't have a battery in the car, and when the battery is used up, then you have to replace the battery. When you hear a fuel cell automobile, you're looking at something like combusting hydrogen gas, and we use that to generate a voltage to run our automobile. Next section gets into corrosion, because corrosion is really a redox reaction, but it's a very negative redox reaction that costs billions and billions of dollars every year. So it'd be nice if we had some reactive metals, if we could do something to prevent them from corroding. Well, if it's a redox reaction, understanding the whole corrosion process really means you've got to understand what's happening with voltaic and electrolytic cells, what's happening with redox reactions. Now, because the standard reduction potential for Fe2 plus, which is our iron ion, is negative 0.44 volts, that's less positive than the reduction potential for oxygen. So that means iron is going to be oxidized by oxygen. So iron in the process, or in the um, presence of oxygen, especially if we've got a drop of water there, because that helps our transfer of electrons and we create a solution that really speeds up this process. So in a wet environment, iron is just going to rust because oxygen is in air. And if the iron in the product becomes exposed to that air, especially in the process of a little bit of water, then you're going to have a relatively rapid, now by rapid I mean it's going to take time. So it's not rapid like quick like burning a piece of paper, but you do set up a situation where the redox reaction, the conversion of iron into Fe2 plus, and the oxidation of the iron by oxygen is going to be a situation that it happens. So what we have to do is a couple of things. One, we have to protect our iron. You paint iron. Well, if the paint is on the exterior coating of the iron, so basically we're looking at coating a reactive metal to help keep the oxygen away. If we coat the metal, then that's something that will end up helping to reduce our amount of rusting. But let's say as you drive your automobile, little tiny bits of sand and grit hit the car and they're constantly wearing away that paint on the microscopic level, eventually it's going to expose the iron, and that's going to allow iron to come in contact with oxygen, and your car is going to rust. Well, you can help that process and prevent it by waxing your car periodically, because that will put another coating on the outside of the paint that will help to protect the oxygen. But eventually, in most situations where we have iron, like in an automobile, eventually you're going to have a situation where oxygen is going to come in contact with that iron and you're going to end up with a redox reaction happening. And it's really because if you look at the reduction cell potentials, the favored reaction is going to be the oxidation of the iron. Now, if that's what causes oxidation, it's a spontaneous reaction when the components come together. What can we do to prevent it besides painting it? Well, there are a number of things we can do besides painting something or coating something to help with corrosion prevention. And in this case, what we're using is zinc, which is a more easily oxidized metal. So if we have a situation where oxygen is going to come in contact with these two things in a similar area, it's much more likely that the zinc is going to be oxidized than the iron is going to be oxidized. So literally, galvanizing an iron nail, putting a zinc coating on the outside of it, will help prevent the iron from rusting, because preferentially zinc is going to be more easily oxidized. So what happens is over time, the zinc is more likely to be oxidized and become zinc oxide on the outside, and that helps protect the iron nail underneath. So galvanization, which is a form of what's known as cathodic protection. You're basically setting up a situation where between zinc and iron is going to be the cathode and zinc is going to be the anode in these reduction reactions. So zinc is going to be the substance that becomes an ion. So cathodic protection is useful in something like the galvanization process, where you have iron and you want to protect it, so you put a thin coating of zinc on the outside. Another way to use cathodic protection, and this is useful in water pipes, because most of the time large water pipes are made out of metals, and those are metals that are going to corrode over time and eventually become weak and spring a leak. Well, what they end up using is cathodic protection. They will bury a magnesium or more reactive anode, and in this situation, if those two things are connected by a copper wire, you set up a situation where this is going to be is going to end up becoming our anode, and that's going to prevent the iron from becoming an anode and rusting. So literally, you sink these magnesium chunks that are connected to our pipe by a copper wire into the ground. And over time, it's the magnesium that is going to slowly rust away and become magnesium oxide, protecting the pipe. The nice thing about this situation is every once in a while we can dig up these magnesium plugs and replace them with fresh magnesium, and that'll end up protecting it. We often do the same thing on the outside of ships. Um, at nuclear power plants, a lot of situations where we have metal in contact from water, we use a more reactive metal in contact with the other one to literally force the iron to become a cathode, and therefore it won't rust. And that's also the case for a galvanized nail. We set up a situation here where the more reactive zinc forces the iron to be the cathode rather than the anode, and we don't get the iron oxidizing. We get the zinc oxidizing. So cathodic protection is something that's incredibly important in many everyday situations. Now, the last section, 20.9, comes into a utilization of electrolytic reactions. There's just a number of times where we want to take and plate a metal on top of another metal, and the reaction itself is not spontaneous. So we can't just dip it in a solution and it spontaneously coats the metal. So what we have to do is use electricity to force a non-spontaneous reaction to occur. And electrolytic cells are what we're looking at. So the process is known as electrolysis. And we use electrolysis to plate a lot of different types of metals, like chrome on a bumper, um, to basically force a non-spontaneous reaction to occur. So voltaic cells are spontaneous reactions, while electrolytic cells, on the other hand, they require electricity to cause a non-spontaneous reaction to happen. Now, the voltage source creates an electron pump. It's a push of electrons towards the cathode away from the anode of the cell. So it reverses really the situation. So that means the cathode in this particular case is going to be negative in an electrolytic cell. So remember, anodes are negative in voltaic cells, but cathodes are negative in electrolytic cells. Now, the negative end of the voltage source is going to be connected to the cathode to provide the electrons for the reduction of sodium in this particular picture here. Now, the electrons that are removed from the oxidation process, the anode, travel to the positive source and complete the circuit. Now, in this case, however, it's not a spontaneous situation, so that electron movement automatically happens. We need a voltage source to push electrons, in essence, uphill and make a non-spontaneous reaction occur. Now, one of the ways in which we use this, and this is really where the math for the last section comes in, is what's known as, quantitative aspects of electrolysis. Quantitative means number. So what we're really looking at is two basic situations. How much metal can be plated out in an electrolysis situation, and how long will it take? Those are usually the two calculations we end up performing with an electrolysis situation. Now, because we're talking about a redox reaction, and the amounts and the electrons pushed in this redox reaction are critical, we're looking at using stoichiometry. So basically in this last section, we're doing another form of stoichiometry. One of many times in this book, we've looked at using stoichiometry. So this is known as electrolytic stoichiometry. So in electrolytic stoichiometry, we're really answering one of these two questions. How long is it going to take us to plate out a certain mass of metal? Or if we let the electrolysis reaction run for this length of time, how much metal can we plate out? Usually we're answering one of those two questions. They're kind of the reverse of each other. Now, one of the things you need to understand to deal with this type of process is the amp. Amp is the SI unit of current. So we're talking about flows of electrons. How long do we have to let this flow of electrons occur to plate out a certain amount of metal? Well, that would be measured in amps. Now, the symbol for amp is I, so be careful of that. And the unit is A. So if it says 16 capital A, then that means 16 amps of current. Now, it's a measure of the amount of charge that passes through a point in a given amount of time. So how much charge are we moving through in a given amount of time? Time is typically seconds. Now, the charge is determined by the number of electrons that are being moved, and that's measured in coulombs. For every mole of electrons that gets moved by a point in time, that's 96,500 coulombs. Remember, this is a Faraday's constant, which is related to how many moles and how many coulombs. So 1 mole of electrons is 96,500 coulombs. So if we push 1 mole of electrons through a given spot in a wire in 1 second, um, you would be looking at basically 96,500 coulombs per second. So 96,500 amps. So basically amps would be coulombs per second. So if we pushed 1 mole of electrons through in a second, that would be 96,500 coulombs per second. That's a lot of amps. Now, the way you're going to see this relationship expressed on the AP constant sheet is I, which is, remember, amps, equals Q over T, and Q is the charge. Now, a more useful way to think about this, because Q, and you think of charge, well, think of coulombs. So think of it as I equals the number of coulombs in a given amount of time. And remember, if we're talking about amps, that would be coulombs per second. But literally, amps is how many coulombs in a given amount of time. So if we want to answer a stoichiometry process or problem, so let's say we're looking at the electrolysis reaction involving aluminum. We have to basically take into account the stoichiometry of the reaction that we're looking at. So we would look at the half reaction for the metal that we're studying, and that half reaction is going to show us how many electrons are needed to basically achieve our electrolytic process. So to turn Al3 plus into Al, we need 3 electrons to make that happen. So for any half reaction, the amount of substance that is reduced or oxidized is directly proportional to the number of electrons that are passing through the cell. This is what's known as Faraday's law, which we don't get into, but that's really what Faraday's law is. So if we are using this chemical reaction, so this is the reduction reaction we're looking at causing to happen, for every 3 moles of electrons that we use, we're going to make 1 mole of aluminum metal. So for every 3 moles of electrons we push into our solution of aluminum nitrate, we're going to end up plating out 3 moles of aluminum. And remember, it's 96,500 coulombs for every 1 mole of electrons. So if we know how many coulombs of charge we've pushed through, we can determine how many electrons that is, and then we can use our balanced equation here to go from moles of electron to moles of aluminum. And that's why this is a stoichiometry process. This idea right here is our bridge between our amount of substance and our number of electrons, which is related to our current flow. So that's why this is a stoichiometry process. And remember, if we can get moles of aluminum, we can use the molar mass of aluminum to find out how many grams of aluminum that is. So really what we're doing here is we're converting back and forth between coulombs and mass. If we know how many coulombs, or can find out how many coulombs, that's the key. That's what I need to teach you, is how do you determine the number of coulombs. We can use stoichiometry to convert to mass, and vice versa. If we know what the mass is, we can use stoichiometry to convert back to coulombs. Now, there's 2 general things. Remember, we were looking at finding out how much could be plated out or how long it's going to take. Well, if we're finding the mass, this is the process we use. We're going to use this equation, which we looked at a second ago. The number of amps is going to equal the coulombs per time. And we're going to use that to establish our coulombs, because they're going to tell us how many amps, and they're going to tell us how many times, or how much time. Remember, we just need to convert that to seconds so we can determine how many coulombs we've got. Well, once we know how many coulombs we've got, we can use stoichiometry to convert that into grams. So first you're going to use this equation to determine the number of coulombs, and then you're going to second use stoichiometry to get the answer. Well, if they're asking how long it's going to take to plate a certain amount of metal, it's just the same thing in reverse. First, we're going to use the stoichiometry to convert our grams to coulombs, and then we're going to use this equation to convert those coulombs and the amount of time that's given into our number of amps. Or, in the case of finding the time, the number of coulombs and the amps to calculate what the time is. So really, we're doing the same exact thing, but just in reverse. So if you know how to do one problem, you know how to do any problem. So here's an example of electrolysis problem. The long and short of it is a whole lot easier than it may be seeming at this point. So watch the process. What mass of aluminum is produced if 10.0 amps is applied for 1.00 hours to an electrolytic cell containing molten aluminum chloride? So we're looking at plating out aluminum in this process. Now, since we're trying to find the mass, remember, first we find the coulombs and then we do the stoichiometry. Well, how do we find the coulombs? Remember, it was the equation I equals the number of coulombs over time. So that means the number of coulombs would be I times the time in seconds. So amps times seconds will give us the number of coulombs. That's really the key. This is what you have to do first. And then the stoichiometry comes in. Now in this particular case, we had 10.0 amps. Now it's given in 1 hour. And remember, amps is the number of coulombs per second. So we have to do our conversion to seconds here. Be careful of that. It's rare that they actually tell you the time in a very short amount of time, like seconds. Usually it's going to be minutes or hours. So you have to convert your time value into seconds and then multiply that by amps and you'll have the number of coulombs. So in this particular case, we've got 3.60 times 10 to the fourth coulombs of charge are being applied. Now here's where the stoichiometry comes in. Now since we're talking about turning aluminum ions into aluminum metal, this is the equation we're going to use. Now we've got coulombs, and remember our Faraday's constant is going to allow us to convert from coulombs to electrons. So here we're just using a constant to convert the number of coulombs into moles of electrons. Then our stoichiometry comes in. Here's our mole ratio. And then finally, we use molar mass to convert our moles into grams. So once we know our coulombs, we convert that to moles of electrons. And then we use the stoichiometry of 3 moles of electrons would equal 1 mole of aluminum. And 1 mole of aluminum is 27.0 grams. So if we apply that amperage for that time to molten aluminum chloride, we would end up plating out 3.36 grams of aluminum. So using that much energy, we can end up producing this much aluminum. Now, if they told us how much aluminum they plated and they wanted to know how long that would take, we just do the process in reverse. We start with our mass, and then we would use molar mass flipped to convert to moles. And then we would go from moles of aluminum, so this relationship here, once again, flipped to get to moles of electrons. And then we would use this flipped to go from moles of electrons to coulombs. And remember, that's a constant. It's on the AP constant sheet. Just got to look it up. And then that would give us how many coulombs. And then at the end, we would go back to that equation. Remember, I equals the number of coulombs in per second. Once we know the number of coulombs, we could then take and manipulate this equation. The time would equal the number of coulombs divided by the number of amps. So remember, our symbol is I, but our unit is going to be A here. So I suppose I should write it that way. So if they give us a mass and they're asking how long it'll take, it's just the exact same thing in reverse. First, you do your stoichiometry to get your number of coulombs, and then you use this same equation. Now solve for the time factor S to get T. And do you know what this means? Since we're at the end of section 20.9, you don't have to listen to any more notes. This is it. So at this point, we're done with our learning of AP. We just need to practice a little bit more to get ready for that AP test. So that ends our very last set of notes for the entire year.